I'm Eric Roots. I'm in the last year, or hopefully less, of my PhD project. I've been working on the MT data along some of the transects as well as some of the larger scale inversion and analysis of the MT data. So today I'll be talking about some hopefully soon to be published results from the southeastern part of the Superior, as well as getting a quick look at some of the work being done with the MT data in the Western Superior. So here is a simplified geological map of the Superior Province. We have our 750 metal earth stations in the white, largely distributed across the 13 transects. We also have some broadband stations from various legacy projects like Lithoprobe and Discover Abitibi, both in the western and eastern side of the Superior, shown in the blue circles, and some long period measurements exclusively in the Western Superior, given by the green circles. And for some of the sort of deeper sensing mantle work being done in the Western Superior, I've also had to rope in some additional long period measurements from the US array data set to the south, a small number of which are shown here by the black circles. So a lot of work has been put into integrating the geology and the various geophysics, including the MT, across each of the transects. But in addition to those sort of more detailed cross sections of the crust, we'd also like to take a look at some of the large scale characteristics of the Superior Province. Obviously, in this case, the large scale resistivity structure of the Superior. But based on the size and the scale of the craton, as well as the distribution of stations we have, it's obviously impossible to tackle this problem all at once. So we've broken it down into some smaller problems. So first I'll show some results from the southeastern part of the Superior in this black box, which is essentially the southern part of the Abitibi as well as part of the Pontiac subprovince. And then at the end, I'll quickly show some stuff from the Western Superior. So zooming into that black box, we have our combined sort of lithoprobe, Discover Abitibi, and Metal Earth MT data, 112 broadband stations in total, mostly distributed across the 4 transects in this region. So we have from west to east, Matheson, Larder Lake, Rouyn-Noranda, and Malarctic. We have the outlines of the 2 major deformation zones here shown by the white dashed line. To the north, the Porcupine Duster, and to the south, the Larder Lake Cadillac deformation zone, along which we find a number of significant deposits, which here are shown by the gold squares. We also have a lot of seismic data in this area, but specifically shown here, the ones used in this particular study are these 4 red lines, 3 from Lithoprobe, line 23, 12, 14, and 16A, as well as the Metal Earth Larder Lake Traverse. So I won't go into detail about the inversions. I'd like to thank Fabiano for already covering what inversion and forward modeling is, so I don't have to. And I'll go right into showing some results from our preferred model of the region. So first, some plan view slices or map view slices through the model, and I'll talk about some of the more important features that we've imaged. So this is a slice at 11 kilometers depth and is fairly representative of the upper crust of the region, consistent with its composition of primarily dry, cold volcanic rocks. We see relatively high resistivities throughout. And even in the regions where we might expect to see some sediments or metasediments, say in the Pontiac subprovince, we see that change in lithology doesn't seem to have a huge effect on the resistivity overall. The obvious exceptions to this generally high bulk resistivity, I've outlined a few, the UC1 to UC5 sort of conductive zones. These are narrow features or collections of features which are typically in the tens or hundreds of ohm meters in terms of resistivity, as compared to the thousands or tens of thousands of ohm meters of the surrounding host rock. So an order of magnitude or 2 less resistive than everything else. And you'll notice that these features tend to be largely clustered around the 2 major deformation zones or their related branches or splays. Jumping down into the mid-crust, the previously sort of narrow conductive zones in the upper crust have merged into these larger, somewhat north-south-ish trending features, and there seems to be pretty much at least one for every transect along Matheson, Larder Lake, Rouyn-Noranda, and Malarctic. And in some cases, these mid-crustal conductors are separated by zones of resistivity, so these R1 and R2 resistive zones. But I should say that based on the spacing of the MT stations, we can't completely rule out that this sort of conductive resistive spacing isn't just an artifact of the survey design. However, the model resolution tests that we did do show that the data that we have is better fit if we include all of these features. Jumping down to the lower crust is my favorite part of the model, as our mid-crustal conductors, which were north-south-ish oriented, sort of morph and form into this more east-west trending structure. So we have an LC1 conductor sort of below and subparallel to the Larder Lake Cadillac deformation zone. Likewise, LC2 sits sort of below and to the north of the Porcupine Duster, and we have this resistive band R3 that sits in between the two zones. So to try to take a better look at all of that in one image, I'll show some depth slices through the model. I'll take a composite section through line 23 here, joining up to the Larder Lake traverse, and then jumping over to line 12 and continuing on to the north, north of the Porcupine Duster. We'll overlay that with the seismic from those lines. So I think this gives a pretty good overview of what was seen throughout the plan view slices. We see the generally resistive upper crust with relatively few reflections throughout. That generally high resistivity upper crust is broken by these subvertical conduits or pipes or whatever you wish to call them, clustered around, in this case, the Larder Lake Cadillac deformation zone. And those coincide with breaks or offsets in the seismic reflections as well. The mid-crust is characterized by generally lower resistivities, as well as the top of that transition coincides with an increase in seismic reflectivity. And then again, my favorite feature or set of features is the generally conductive lower crust or upper mantle zone, characterized by the LC1 and LC2 conductors and broken by this R3 resistive zone. And the reason it's interesting, I think, is that I think the orientation and the geometry of these three features gives us some clues as towards the tectonic history of the region. While it's possible that this lower crust and upper mantle region was once uniformly resistive, and something might have happened to cause this LC1 and LC2 zone to become conductive, based on the fact that R3 sort of cross-cuts these two features, makes it more likely, I think, that R3 postdates the conductivity of the upper mantle. So with that in mind, we can draw some interpretations from this model, which might look something like this. So on the left-hand side, we see a geological interpretive series of events. And on the right-hand side, we see sort of a cartoony version of the geophysical signature that we see today, which would be analogous to the slice we saw back here. And so the interpretation would go something like this. During the late stages of construction of the Southeastern Superior, we have perhaps a slab breakoff or delamination event, which drives upwelling fluids and melts upwards towards the lower mantle, or sorry, upper mantle, lower crust. These fluids and magmas could melt the enriched upper mantle, and this melting would liberate incompatible and ore-forming elements from the enriched zone and propagate further upwards through mid-crustal and upper crustal zones of weakness. As these enriched fluids travel upwards, they would precipitate out carbon and possibly sulfides in the mid and upper crustal pathways through which they travel. And then relatively undisturbed in the craton since then, in the 2 or 3 billion years since then, the solid conductive phases in the form of graphites and sulfides would remain deposited in the mid and upper crust. And likewise, the now cold and depleted zone of melt in the lower crust and upper mantle would remain today, as we see the R3 zone in the upper mantle and lower crust, and then those mid-crustal and upper crustal conductors. So that's a brief tour through the model and the interpretations of the MT data in the Southeastern Superior, and I'd like to just completely shift gears and go over to the Western Superior now quickly. Given that the majority of the data here is long period, and the spacing of our stations is quite a bit higher in general than it is in the Abitibi, the results are more concerned with the deeper structure in the mantle than it is necessarily with the crust. And because of the depths we're looking at and the long period data that we have, I've had to incorporate some more data further to the south from the US Array MT data set, again with these black circles, to make sure that the aperture of our data set was sufficient to actually be able to image mantle structures properly. In the interest of time, I'm just going to be talking about one specific aspect of the data and the modeling concerning the sort of the central block of the Western Superior here in this black box. So in one of the earlier board meetings, I think I showed a plot that looked like this. These are called phase tensor plots or phase tensor ellipses. Basically what we're looking at is a representation of the MT data where the orientation of the ellipse, the shape of the ellipse, and the color tells us something about the polarization, direction, and amplitude of the electromagnetic fields, which in turn tells us something about the conductivity contrasts and orientations of the structures at particular depths. So for instance, this is a plot at a period of 20 seconds. We can see that the ellipses aren't really consistent. There's no consistent facing or direction as we move across the Western Superior. And this is telling us that each station at this period is likely sensing its own relatively local crustal structure, probably in the mid to lower crust. But as we go to longer periods or equivalently deeper depths at 40 seconds, 80 seconds, 160 seconds, you can see that there's sort of a mass realignment of the ellipses in this central block where they all start to turn sort of east-west, as well as all getting darker. And this is telling us that there's a significant contrast in the east-west versus north-south conductivity structure in the mantle, which seems to run sort of from the western edge of the craton before perhaps fading out a little bit here beneath Lake Nipigon. So many inversions were performed on this data set and subsets of it to try to figure out what could be causing this kind of data. And I'll just quickly show you a slice through the preferred model at this point that could be an explanation for this. So this slice is at 147 kilometers, so right in the mantle. We can see that it images a series of alternating conductive and resistive bands, again, pretty much from the western edge of the craton before we get this faded, sort of twisted one through Lake Nipigon. And while these features are pretty striking, this sort of feature imminent inversion, as well as the data that I showed, can also be indicative of electrical anisotropy. And so we have to ask ourselves, what's the more likely scenario here? That the mantle of the Western Superior is characterized by these sort of alternating conductive resistive mantle dike-like structures, or that the mantle is electrically anisotropic. We get a bit of extra evidence in favor of anisotropy from some seismic receiver function studies. So this is a plot from one in Romanowitz, which shows the seismic fast axis direction on the left and the magnitude of anisotropy on the right. And we can see for the plot on the left, between 100 kilometers and 200 kilometers depth, the seismic fast axis is pretty much north-south. As this is pretty much the exact depth interval and orientation of our apparent electrical anisotropy, this would be the favored explanation at this point. Which of course raises the next question, which is what could be causing this sort of seismic and electrical anisotropy? And for the seismic data, the explanation that's typically invoked is lattice preferred orientations, or LPOs, of olivine crystals in the mantle, which among other things may be related to the deformational history of a region, including the presence and direction of ancient or modern subduction zones. However, before we can draw any conclusions about Archean subduction in the Western Superior, some additional forward modeling needs to be done with the MT data to constrain the magnitude of electrical anisotropy that the data supports, as above a certain value, lattice preferred orientations are no longer sufficient to explain that sort of data. So to summarize all of that, we took a look at the MT model in the Southeastern Superior, which was characterized by a resistive upper crust intruded by clusters of conductive pipes, conductive mid-crust, and higher reflectivity in the mid-crust, and that east-west trending LC1, R3, LC2 resistivity pattern in the lower crust and upper mantle. And we interpret this structure to represent relic, source, and transit domains and crustal pathways enriched by the flow of magmas and or metamorphic fluids throughout the Southeastern Superior, possibly related to a late-stage pulse of ore-bearing magmatism as a result of slab breakoff or delamination. And then over in the Western Superior, we saw some north-south oriented geoelectric structure in the mantle, which I believe is likely related to electrical anisotropy in the Western Superior and possibly related to Archean subduction zones in that area. And so with that, I'll thank you for your attention.
Great, thanks very much, Eric. We have some questions.
Yeah, Eric, have you come in terms of the Western Superior, the Midcontinent Rift that is much more recent could have affected well?
I only got part of that because of the mic that I think you're asking about the Midcontinent Rift.
Mm-hmm.
Yeah, that's one of the reasons I think why we see this, the alignment of these structures kind of stops beneath Lake Nipigon, and I'm wondering if that has to do with some effect of the Midcontinent Rift, which I believe kind of comes up beneath Lake Superior and possibly extends into this region. So if it is anisotropy, then it is possible that the MCR could be sort of breaking up that structure east of Lake Nipigon.
Mm-hmm. It's also like a lot of intrusion of sills related to the Midcontinental Rift if seen through Lake Nipigon. So it's not just like the Superior region, it goes as far north as Nipigon.
Mm-hmm. Yeah, I think it comes up at least to around there.
Yeah, that's right. Yeah.
Yeah. Yeah, it's definitely a possibility that we're looking at to try to explain why, the phase centers in this region are all pretty much facing one direction, but once you hit Lake Nipigon, you get a different facing.
Mm-hmm.
Eric, can I ask a short question? Can you go back to the UR3 feature on where you have the seismic MT overlay? Yeah. Is this? I was just wondering so the seismic reflection, the reflection profile is that cut off there in the R3 area, or it's such a sharp contact?
It's the Larder Lake data only goes to about that depth, whereas the lithoprobe data was processed slightly differently, so it goes a little bit deeper.
Because you still have reflections down after 40 kilometers depth though in that zone, but it's really...
Yeah, you can't really see it here, but the if we used only line 12, which doesn't quite overlap with the empty stations, which is why we used the Larder Lake one instead. But the reflections in line 12 do actually sort of form a dome shape under here, which also kind of plays into the interpretation of a bit of underplating at the base of the crust.
Oh, I see. Okay, good. I was just wondering.
Mm-hmm.
All right, we better continue on. Thank you very much, Eric.